universe is a place of infinite wonder, governed by a set of elegant and unyielding laws. These laws, the principles of physics, are the invisible threads that weave together the fabric of reality, shaping everything from the smallest subatomic particle to the largest galaxy. They dictate the birth and death of stars, the motion of planets, contemplate the physics of the universe is to step into a world where the ordinary becomes extraordinary, where the mysteries of existence unfold in patterns of breathtaking complexity. Did you know that the speed of light is not just a limit but a cosmic constant that underpins the very structure of space and time? Or is gravity, the force that holds us to the Earth, also responsible for the formation of galaxies and the bending of light across billions of light years? The laws of physics are universal, applying everywhere and at all times, whether we are studying the motion of electrons in an atom or the collision of black holes in deep space. These laws remain the same. The universal nature of physics. At its core, physics is the study of how the universe works. It is the science that seeks to explain the fundamental nature of reality, from the smallest particles that make up matter to the grandest structures of the cosmos. It is the language of the universe, a discipline that connects the behavior of matter and energy to the forces that govern them. Physics provides the framework for understanding phenomena on every scale, whether the intricate patterns of a snowflake or the majestic rotation of a spiral galaxy millions of light years away. Did you know that the same gravitational force keeping your feet firmly on the ground is responsible for the moon's orbit around Earth and the motion of the planets around the sun? This profound universality is one of the most astonishing aspects of physics. The laws we uncover here on Earth apply equally to the most distant corners of the universe. Whether it's the gravitational pull between stars in a distant galaxy or the way a ball falls to the ground when dropped, the same fundamental principles are at work. This consistency makes physics a science of exploration and a tool for discovery, allowing us to predict and understand events far beyond our immediate surroundings. Even the most ordinary moments of our daily lives are shaped by the principles of physics. Consider the sunlight that warms your skin. That warmth results from nuclear fusion occurring deep within the sun's core, where hydrogen atoms collide and fuse into helium, releasing energy in the form of light and heat. The sun's light travels approximately 93 million miles through the vacuum of space, taking about 8 minutes to reach Earth. When it arrives, it nourishes plants, powers weather systems, and sustains life. A remarkable journey governed by energy and electromagnetic radiation laws. The colors of a rainbow after a rainstorm are another stunning example of physics at work. A rainbow forms when sunlight passes through raindrops, which act as tiny prisms. The light is bent or refracted as it enters the raindrop and separates into its component colors: red, orange, yellow, green, blue, indigo, and violet. The different colors emerge because each wavelength of light bends by a slightly different amount. This simple yet elegant interaction between light and water is governed by the principles of optics, a branch of physics that explains how light behaves when it encounters different materials. The sounds that fill our world, whether it's the gentle rustle of leaves, the hum of a car engine, or the melody of a favorite song, are also shaped by physics. Sound is a vibration that travels through the air, or other mediums, as a wave. These sound waves are compressions and rarefactions of air molecules, and their frequency determines the pitch we hear. For instance, when you listen to music, the guitar strings or the vibrations of a singer's vocal cords set air molecules into motion. These waves eventually reach your eardrum, where they are translated into signals your brain can understand. Every note and every rhythm is made possible by the laws of acoustics. demonstrating how physics turns vibration into melody. Physics is not just a science of explanation, but a science of wonder. It asks some of the most profound questions. Why does the universe exist? How did it begin? What are its fundamental building blocks? And how will it end? These questions drive the work of physicists, who use experimentation, observation, and mathematical models to peel back the layers of reality. Consider, for example, the theory of general relativity, one of the most significant achievements in physics. Proposed by Albert Einstein in 1915, general relativity revolutionized our understanding of gravity by describing it not as a force, but as the curvature of space-time caused by mass and energy. This theory explains the motion of planets and the bending of light around stars, and predicts phenomena like black holes and gravitational waves. Gravitational waves, ripples in the fabric of space-time caused by massive cosmic events, were first directly detected in 2015, a century after Einstein's prediction. These waves are produced when massive objects like black holes collide or neutron stars spiral into one another. The detection of gravitational waves opened a new window into the universe, allowing us to observe previously invisible events. It also underscored the power of physics to turn abstract equations into tangible discoveries, expanding our understanding of the cosmos. Another cornerstone of physics is quantum mechanics, which governs the behavior of particles at the most minor scales. While classical physics explains the motion of planets and the flow of rivers, quantum mechanics delves into the realm of atoms and subatomic particles, where reality becomes strange and counterintuitive. Particles can exist in multiple states simultaneously, a phenomenon known as superposition, or become entangled, meaning their states are interconnected even across vast distances. Quantum mechanics underpins our understanding of matter and energy and forms the basis for technologies like semiconductors, lasers, and even the emerging field of quantum computing. Physics also bridges the gap between the microscopic and the macroscopic, revealing how the minor components of reality give rise to the most significant structures in the universe. For example, the atoms that make up your body were forged in the cores of ancient stars. When those stars exhausted their fuel and exploded as supernovae, they scattered these elements into space and eventually coalesced into new stars, planets, and ultimately, life. The fact that every atom in Uadi has traveled through billions of years and countless cosmic processes is a testament to the interconnectedness of all things, a theme that physics constantly reinforces. The study of physics has also revolutionized our technological landscape. From the discovery of electromagnetism, which led to the development of electric power and communication systems, to the principles of thermodynamics that power engines and refrigeration, physics has reshaped how we live. Even modern marvels like GPS systems rely on the principles of relativity to function accurately. As in this way, physics helps us understand the universe and improves our daily lives, bridging the gap between the theoretical and the practical. Yet, physics retains a certain simplicity and elegance for all its complexity. Though mathematically intricate, its laws often reveal profound truths in straightforward ways. For instance, Newton's laws of motion can be described in 3 simple statements, yet they explain everything from the fall of an apple to the trajectories of spacecraft. This blend of simplicity and depth makes physics captivating. It provides clarity while leaving room for wonder. As you look around the world, you'll find that physics is everywhere. The way water flows in a stream, the flicker of a candle's flame, the patterns of frost on a windowpane. The laws of physics shape all these phenomena. Even walking involves a complex interplay of forces, from gravity pulling you down to the friction between your shoes and the ground propelling you forward. Physics is not just a distant or abstract science. It is woven into the fabric of everyday life, reminding us of our connection to the universe. In the end, physics is more than just the study of how things work. It is a journey into the heart of reality itself. It reveals the beauty of the universe, the elegance of its laws, and the profound interconnectedness of all things. Whether we are gazing at the stars, marveling at the colors of a rainbow, or pondering the mysteries of black holes, Physics invites us to explore, question, and wonder. It reminds us that we are not separate from the cosmos, but integral to its grand story. And in that story, there is endless inspiration to be found. The language of the universe. Physics is often called the language of the universe, and for good reason. Its laws are equations and mathematical statements describing the relationships between forces, motion, energy, and matter. These equations are not mere abstractions. They are tools that allow us to predict and understand the workings of the cosmos. Consider this. Did you know that the equation E equals m2o equals mc to the power of 2, Einstein's famous formula, revealed that matter and energy are interchangeable? This single insight not only transformed our understanding of the universe, but also laid the foundation for technologies like nuclear power and even the GPS systems we use daily. Mathematics allows us to explore the universe's most profound mysteries. It will enable us to calculate planet orbits, understand the behavior of light, and even peer into the distant past by studying the faint glow of the cosmic microwave background radiation, the afterglow of the Big Bang. The harmony of forces. The universe is governed by four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Each plays a distinct role, yet together they create the intricate balance that allows the cosmos to exist as it does. Gravity is the force of attraction between masses. It shapes the orbits of planets, binds galaxies together, and even bends light around massive objects in a phenomenon called gravitational lensing. Electromagnetism governs the behavior of charged particles, enabling light to travel across the cosmos and causing phenomena like electricity, magnetism, and sunset colors. The strong nuclear force holds the nuclei of atoms together, making it the force that allows stars to shine by enabling nuclear fusion. The weak nuclear force governs processes like radioactive decay, playing a key role in forming star elements. Did you know that without the precise balance of these forces, the universe as we know it could not exist? If gravity were slightly stronger, stars might burn out too quickly. Galaxies might never have formed if they were weaker. Physics and the infinite cosmos. Physics explains the universe and reveals its profound interconnectedness. Every star, particle, and ray of light is part of a grand cosmic symphony governed by the same unchanging principles. Did you know that the observable universe spans 93 billion light years, yet all of it operates under the same physical laws? This consistency allows scientists to predict phenomena that occurred billions of years ago or billions of light years away. As we delve deeper into the universe's physics, we uncover a story of immense complexity and simplicity. From the dance of subatomic particles to the motion of galaxies, the universe is a place of order and chaos, symmetry and spontaneity. The beauty of understanding, physics offers more than explanations. It provides perspective. It reminds us that we are part of something far more significant than ourselves, connected to the stars and the galaxies through the elements that make up our bodies. It is a science of wonder, curiosity, and discovery, inviting us to see the universe not as an incomprehensible void, but as a place of beauty, harmony, and possibility. Let us now embark on a journey through the physics of the universe, exploring the forces, phenomena, and principles that shape everything we see and everything we cannot. The forces that shape the universe. The universe is a dynamic tapestry where matter and energy move, transform, and interact. At the heart of this complexity lie the four fundamental forces of nature. These forces are the architects of the cosmos, shaping everything from the formation of galaxies to the behavior of the tiniest particles. Gravity, the force that binds the cosmos. Of all the forces in the universe, gravity is the one we experience most directly. It is the force that keeps our feet on the ground, holds planets in orbit, and binds galaxies together. But gravity is more than just a force of attraction. It is a fundamental property of space and time. Einstein's general relativity described its own as the aspect of gravity. As Albert Einstein described, gravity is not a pull between objects, but a warping of space-time. Massive objects like stars and planets curve the fabric of space-time, creating what we perceive as gravity. Did you know that this warping of space-time allows light to bend around massive objects, creating phenomena like gravitational lensing? This effect has been used to discover distant galaxies and even exoplanets. The scale of gravity. Gravity operates on all scales, from the tiny pull between two grains of sand to the immense force binding entire galaxy clusters. Without gravity, the universe would be a chaotic expanse of unstructured matter. Stars would not form, planets would not orbit, and galaxies would not exist. Electromagnetic force, the light of the universe. The electromagnetic force governs the interaction of charged particles and is responsible for some of the most familiar phenomena in our daily lives. The force behind light, electricity, and magnetism shapes how we experience the universe. How it works. The electromagnetic force arises from the exchange of photons and light particles. These photons mediate the interaction between charged particles, creating forces of attraction or repulsion. Did you know that every time you see light, you are witnessing the action of photons traveling across space? The role in the universe, electromagnetic waves allow energy to travel through space, from the warmth of the sun to the light of distant stars. This force is also responsible for the structure of atoms and molecules, holding electrons in orbit around nuclei and enabling the chemical reactions that make life possible. The strong nuclear force. The universe's glue. The strong nuclear force is the most potent in the universe but operates over the smallest distances. It binds protons and neutrons together in the nucleus of an atom, overcoming the repulsive force between positively charged protons. Star power. Did you know that the strong nuclear force powers stars? In their cores, hydrogen atoms are fused into helium, releasing the energy that makes stars shine. This process, known as nuclear fusion, fuels the sun and provides the light and heat necessary for life on Earth. The force of creation. The strong nuclear force also played a key role in the early universe, allowing the formation of the first atoms. Without it, the universe would be a diffuse cloud of particles, unable to form the structures we see today. The weak nuclear force, the catalyst for change. Although the weak nuclear force is less familiar than gravity or electromagnetism, it is no less essential. It governs radioactive decay, where unstable atoms transform into more stable forms, releasing energy and particles. The role in stars. The weak nuclear force is a key player in the fusion processes that occur in stars. Its life cycle star enables the creation of elements like carbon, oxygen, and iron, which are the building blocks of planets and life. The force of transformation. Did you know that the weak nuclear force is responsible for the radioactive decay that keeps Earth's interior warm? This heat drives plate tectonics and volcanic activity, shaping the planet's surface. The interplay of forces. While each force has its unique role, the universe's beauty lies in their interplay. Together, these forces create the conditions necessary for the cosmos to exist as it does. Gravity brings matter together, forming stars and galaxies. The electromagnetic force governs light and heat, enabling the chemistry of life. The strong nuclear force powers stars, forging the elements in their cores. The weak nuclear force drives transformation, creating the diversity of matter we see today. Did you know the universe would drastically differ without this precise balance? If gravity were slightly stronger, stars would collapse into black holes. And if the strong nuclear force were weaker, atomic nuclei would not form. The cosmos exists in perfect harmony, a testament to the elegance of physics. The forces that connect us. The forces that shape the universe are not just abstract concepts. They are the threads that connect us to the cosmos. Every breath we take, every beat of our hearts, is made possible by the same forces that light the stars and move the galaxies. As we continue our journey, let us delve deeper into one of the most profound concepts in physics, space-time. The very fabric of reality itself. Space-time. The fabric of reality. Space and time are often considered separate entities, the dimensions through which we move and the moments that mark our lives. But they are inseparably intertwined in physics, forming a single dynamic fabric known as space-time. Albert Einstein's theory of general relativity introduced this concept, revolutionizing our understanding of the universe. Space-time is not a passive stage on which cosmic events unfold. It is an active participant, shaped by matter and energy. It bends, stretches, and warps, creating the paths along which objects travel and the rhythms by which time flows. Did you know that the passage of time is not constant? It can speed up or slow down depending on the strength of gravity or the motion of an object. This phenomenon, known as time dilation, is one of the many ways space-time reveals its profound and counterintuitive nature. Einstein's vision, general relativity and the curvature of space-time. Albert Einstein's theory of general relativity, published in 1915, introduced a groundbreaking idea. Gravity is not a force in the traditional sense, but a consequence of the curvature of space-time. The warping of space-time. Massive objects like stars and planets create indentations in the fabric of space-time. These curves determine the motion of other objects, guiding them along curved paths. For example, the Earth orbits the Sun not because an invisible force pulls it, but because it follows the space-time curve created by the Sun's mass. Gravitational lensing, the warping of space-time, also bends the path of light. This phenomenon, called gravitational lensing, allows us to observe distant galaxies magnified and distorted by the gravity of closer objects. Did you know that gravitational lensing was one of the first evidence supporting Einstein's theory? During a 1919 solar eclipse, scientists observed starlight bending around the Sun, confirming his predictions. Time dilation, the fluidity of time, as we experience it, seems steady and unchanging, yet in the realm of space-time, it is anything but. Time dilation, the stretching or compression of time, is one of the most fascinating consequences of general relativity. Gravity's effect on time. In regions of strong gravity, time flows more slowly compared to areas of weaker gravity. For example, a clock placed at the surface of a neutron star, an incredibly dense remnant of a supernova, would tick far more slowly than a clock on Earth. Time and speed. Time dilation also occurs when objects move at speeds approaching the speed of light. An astronaut traveling near light speed would age more slowly than those left behind on Earth. This effect has been confirmed through experiments with atomic clocks on fast-moving jets and satellites. Did you know that astronauts aboard the International Space Station experience time dilation? Because they move at high speeds and are slightly farther from Earth's gravity, their clocks run somewhat faster than those on the planet's surface. The shape of the universe. The shape of space-time is not just a local phenomenon, it also describes the overall geometry of the universe. Flat, open, or closed. The universe could be flat, where parallel lines remain parallel and the fabric of space-time extends infinitely. It could be closed, curving like the surface of a sphere, where traveling far enough in one direction would bring you back to your starting point. Or it could be open, curving like a saddle, with parallel lines diverging over vast distances. What we know. Observations of the cosmic microwave background radiation suggest that the universe is flat on large scales. However, local distortions and the influence of dark energy add complexity to this picture. Ripples in space-time. Gravitational waves. Space-time is not static. It can ripple and vibrate, creating waves that travel across the universe. These gravitational waves, predicted by Einstein and first detected in 2015, are produced by some of the most violent events in the cosmos. Sources of gravitational waves are created when massive objects, like black holes or neutron stars, collide or merge. These waves travel at the speed of light, carrying information about their origins and the nature of space-time itself. Detecting gravitational waves, observatories like LIGO and Virgo use incredibly sensitive instruments to detect the faint distortions caused by passing gravitational waves. Did you know that gravitational waves were first detected after merging two black holes over 1 billion light-years away? Gravitational waves have opened a new window into the universe, allowing us to observe previously invisible events and explore the nature of space-time in unprecedented ways. Space-time and the nature of reality. Space-time is more than just the backdrop of the universe. It is the stage on which the cosmic drama unfolds. Its curvature guides the motion of planets and stars. Its ripples carry the echoes of cosmic collisions, and its fluidity reshapes our understanding of time. Did you know that we are all part of this fabric? Every movement and moment is a thread in the vast tapestry of space-time, connecting us to the stars, the galaxies, and the universe. As we continue our journey, let us explore the universe's most minor scales, the quantum realm, where particles dance in patterns that defy our everyday understanding. The quantum realm, the universe at its smallest scale. At the heart of the universe lies a world that is as puzzling as it is fundamental, the quantum realm. This is the domain of the tiniest particles, where the familiar rules of physics give way to phenomena that challenge our understanding of reality. Particles exist in multiple states simultaneously, entangle across vast distances, and behave as particles and waves. The quantum world operates on scales so small that they defy ordinary perception. Yet it is here that the building blocks of matter and energy reside, governing everything from the structure of atoms to the life cycles of stars. Did you know that the very particles that make up your body are subject to these strange quantum rules? Every breath you take is a dance of particles and waves, a quantum performance unfolding at the most minor scales of existence. What is quantum mechanics? Quantum mechanics is the branch of physics that describes the behavior of matter and energy at the most minor scales, smaller than atoms, where particles like electrons, photons, and quarks reside. At this level, the deterministic rules of classical physics no longer apply, replaced by probabilities and uncertainties. Wave-particle duality. In the quantum realm, particles like electrons and photons can behave as both particles and waves. Did you know that light, which appears as a steady stream, is actually made of tiny particles called photons that also behave like waves? This duality is what allows light to create interference patterns, a phenomenon famously demonstrated in the double-slit experiment. The uncertainty principle, the Heisenberg uncertainty principle, states that we cannot simultaneously know a particle's exact position and momentum. This inherent uncertainty is not a limitation of measurement, but a fundamental property of nature. This principle gives rise to the strange behavior of particles, which exist as probabilities rather than definite states until they are observed. Quantum superposition. Particles can exist in multiple states simultaneously, a phenomenon known as superposition. For example, an electron can be in two different energy states simultaneously until it is measured. This concept is famously illustrated by Schrödinger's cat, a thought experiment in which a cat in a box can be both alive and dead until the box is opened. Entanglement, spooky action at a distance. One of the most intriguing phenomena in quantum mechanics is entanglement, a mysterious connection between particles. When two particles become entangled, their properties are linked so that a change in one particle instantly affects the other, no matter how far apart they are. Einstein's spooky action, famously called entanglement, spooky action at a distance, because it seemed to defy the limits of space and time. Despite his skepticism, numerous experiments have confirmed entanglement. Applications of entanglement, quantum entanglement, is the basis for emerging technologies like quantum computing and quantum cryptography, which promise to revolutionize information processing and security. Did you know that entanglement has been used to teleport quantum information over long distances? This quantum teleportation is not science fiction. It is a real and active area of research. Quantum fields, the invisible foundations of reality. Quantum mechanics goes beyond particles. It introduces the concept of quantum fields, which are fundamental to our understanding of reality. What are quantum fields? Instead of thinking of particles as tiny points in space, quantum field theory describes them as excitations or ripples in underlying fields that permeate the universe. For example, the Higgs field is responsible for giving particles mass, while the electromagnetic field governs the behavior of photons. The role of quantum fields in the universe. Quantum fields are the foundation of the standard model of particle physics, which describes all known particles and their interactions, except gravity. Did you know that every particle you've ever encountered is a tiny disturbance in an invisible quantum field? These fields are everywhere, constantly interacting and shaping the universe. The quantum vacuum, empty but full. Even in the absence of matter, the quantum realm is never truly empty. The quantum vacuum is a place of constant activity where virtual particles momentarily appear and disappear. Zero-point energy, ZRMP. The quantum vacuum is filled with zero-point energy, the lowest possible energy state of a quantum system. This energy is not something we can directly observe, but its effects can be seen in phenomena like the Casimir effect, where two plates placed very close together are drawn together by the vacuum's energy. The role in cosmology in the quantum vacuum played a critical role in the early universe, driving the rapid expansion of cosmic inflation. Did you know that some theories suggest dark energy, which drives the accelerated expansion of the universe, could be linked to the energy of the quantum vacuum? The quantum universe, a mystery we're still exploring. The quantum realm is a place of paradox and possibility, a world where reality behaves in ways that defy intuition. Yet it is also the foundation of everything we know, the invisible framework that shapes the universe at every level. Did you know that even today, physicists are still uncovering the mysteries of quantum mechanics? And from the search for a unified theory of quantum gravity to the development of quantum technologies, the quantum realm continues to challenge and expand our understanding of the cosmos. As we leave the minor scales behind, let us turn our attention to the universe's grand structure, the vastness of space, and the forces driving its expansion, the expanding universe and the role of physics. The universe is not static. From the smallest particles to the most significant cosmic structures, everything in the cosmos is in motion. But perhaps the most profound motion of all is the expansion of the universe itself, a phenomenon that has shaped the cosmos since its very beginning. Did you know that every galaxy we see, except for a few bound by gravity, moves away from us? The farther away a galaxy is, the faster it appears to recede. This discovery, made nearly a century ago, revealed that the universe is dynamic and ever-changing, challenging our understanding of space, time, and the nature of reality. The Big Bang. The birth of the universe. The story of the expanding universe begins with the Big Bang, which marked the birth of space, time, and matter. Approximately 13.8 billion years ago, the universe was an incredibly hot and dense point, smaller than an atom, containing all the energy and matter that would eventually form galaxies, stars, and planets. The first few moments, in the first fraction of a second, the universe underwent a rapid expansion known as cosmic inflation, growing exponentially. This process smoothed out the universe and laid the foundation for today's large-scale structures. Did you know that during inflation, the universe expanded faster than the speed of light? While this might seem impossible, it's important to note that space expanded, carrying matter and energy, cooling and formation. As the universe expanded, it also cooled, allowing the first subatomic particles, quarks, electrons, and neutrinos, to form. These particles eventually combine to create protons and neutrons, the building blocks of atoms. By the time the universe was a few 100,000 years old, it had cooled enough for hydrogen and helium atoms to form. This era, known as recombination, also marked the release of the cosmic microwave background radiation, a faint glow that still permeates the universe today. Hubble's law, the discovery of expansion. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery: the universe expands. By studying the light from distant galaxies, Hubble found that their wavelengths were stretched, a phenomenon known as redshift. What is redshift? As light travels through expanding space, its wavelength stretches, shifting toward the red end of the spectrum. The greater the redshift, the faster a galaxy is moving away from us. This relationship between distance and speed is described by Hubble's law, which states that a galaxy's recession velocity is proportional to its distance from Earth. The implications of expansion. Hubble's discovery showed that the universe is not static, but dynamic, with galaxies moving apart as space itself expands. Did you know that this expansion means the universe was once much more minor, denser, and hotter? A direct confirmation of the Big Bang Theory? Dark energy, the mysterious force accelerating expansion. For much of the 20th century, scientists believed that the universe's expansion was slowing down due to gravity. However, observations in the late 1990s revealed something unexpected. The expansion is not slowing, it is accelerating. This acceleration is driven by a mysterious phenomenon called dark energy. What is dark energy? Dark energy is thought to make up about 68% of the universe, yet its nature remains one of the greatest mysteries in physics. It is often described as a property of space itself, a kind of energy that arises simply because space exists. The role of dark energy exerts a repulsive force, counteracting gravity and causing galaxies to move away from one another at an increasing rate. Did you know that the discovery of dark energy earned the 2011 Nobel Prize in Physics? It has reshaped our understanding of the universe's fate, suggesting that it may expand forever. Theories and unanswered questions. Is dark energy constant, or does it change over time? Could it be linked to quantum vacuum energy or a new field of physics? These questions remain unanswered, keeping dark energy at the forefront of cosmological research. The fate of the universe. The expansion of the universe raises profound questions about its ultimate fate. Will it expand forever, or will it one day contract? While many possibilities exist, current observations suggest a future dominated by dark energy and perpetual expansion. The Big Freeze. If the universe continues to expand indefinitely, galaxies will move so far apart that their light will no longer be visible. Star formation will cease as gas and dust are depleted, and existing stars will burn out, leaving behind only cold remnants like white dwarfs and black holes. Over trillions of years, even black holes will evaporate through Hawking radiation, leaving a dark, empty universe. A scenario known as the Big Freeze, the Big Rip. If dark energy grows stronger over time, it could tear the universe apart in a big rip, where galaxies, stars, planets, and even atoms are destroyed by the accelerating expansion. The Big Crunch. If dark energy weakens or reverses, the universe's expansion could slow and eventually stop, causing it to collapse back into a hot, dense state. This scenario, called the Big Crunch, could lead to another Big Bang, starting the cycle anew. The expanding universe as a window into the past. As we observe the universe's expansion, we are also looking into the past. The light from distant galaxies carries information about the early cosmos, allowing us to piece together its history and evolution. Did you know that the farther we look into space, the farther back in time we see? The light from the most distant galaxies began its journey billions of years ago, long before our solar system even formed. A universe in motion. The expanding universe is a testament to the dynamism of the cosmos, a place where nothing is static and everything is in motion. It reminds us that the universe is not just a collection of objects, but a living, evolving entity shaped by forces we are only beginning to understand. As we continue our journey, let us explore the lives of stars and black holes, cosmic phenomena that reveal the transformative power of the universe's physics. The physics of stars and black holes, cosmic engines and mysterious titans. Stars are the cosmic engines of the universe, celestial forges that transform the raw materials of space into the elements of life. They illuminate the vast darkness, power the galaxies, and serve as the creative force behind the intricate cosmic dance. From their fiery births in nebulae to their spectacular deaths in supernovae and black holes, stars are not just objects. They are processes constantly shaping and reshaping the universe. Black holes, on the other hand, represent the ultimate mystery. Born from the catastrophic collapse of the most massive stars, these enigmatic objects defy our understanding of physics. They are regions where gravity becomes so intense that the very fabric of space-time is twisted and torn, where light itself is trapped, and where the known laws of nature break down. Together, stars and black holes embody the transformative power of the cosmos. a cycle of creation, destruction, and renewal that drives the evolution of the universe. The birth of stars, cradles in the cosmos. Stars are born in vast stellar nurseries called nebulae, sprawling regions of interstellar gas and dust. These cradles of creation are the starting points for stars, where gravity and pressure work together to transform chaos into structure. The collapse of a cloud. Over time, regions within a nebula become denser, often triggered by external forces like a nearby supernova explosion. Gravity takes hold, pulling gas and dust inward. As the cloud collapses, it begins to spin, flattening into a rotating disk with a hot, dense core at its center. This core, known as a protostar, marks the earliest stage of a star's life. Ignition, the birth of a star. When the temperature and pressure in the core reach critical levels, nuclear fusion ignites. Hydrogen atoms are fused into helium, releasing immense energy in the process. This energy pushes outward, balancing the inward pull of gravity and stabilizing the star. The result is a luminous object, a star, shining steadily in the vastness of space. Did you know that the Sun, our own medium-sized star, began its life about 4.6 billion years ago in a nebula similar to the Eagle Nebula? Its steady light and heat have made life on Earth possible, showcasing the profound impact of stellar birth. The life of a star is determined by its mass, which dictates how it burns its fuel and how long it will shine. And its shine. Stars may appear eternal to us, but their lives are finite, ranging from a few million to tens of billions of years. Low-mass stars. The quiet burners, small stars like red dwarfs, are the most common stars in the universe. They burn their hydrogen fuel slowly, glowing faintly for tens to hundreds of billions of years. These stars are so efficient that none have yet reached the end of their life in the universe's 13.8 billion year history. Medium-mass stars, the story of the Sun, stars like our Sun, live for about 10 billion years, spending most of their life in the main sequence, where hydrogen fusion powers their cores. Over time, they slowly grow hotter and brighter, eventually exhausting the hydrogen in their cores and transitioning into red giants. High-mass stars, the cosmic giants, massive stars many times the size of the Sun, live fast and die young. They burn through their fuel in just a few million years, emitting immense light and heat. These stars act as the universe's factories, forging heavier elements like carbon, oxygen, and iron in their cores. Did you know that the color of a star indicates its temperature? Blue stars are the hottest, burning at tens of thousands of degrees, while red stars are more fabulous, burning at just a few thousand degrees. The death of stars, a spectacular finale. The end of a star's life is as diverse as its beginning, determined once again by its mass. Low-mass stars, white dwarfs. When a sun-like star exhausts its hydrogen, it swells into a red giant before shedding its outer layers, forming a beautiful planetary nebula. The remaining core becomes a white dwarf, a dense, Earth-sized remnant that shines faintly as it slowly cools over billions of years. High-mass stars, supernovae and neutron stars, massive stars in their lives in spectacular explosions known as supernovae, briefly outshining entire galaxies. The core of the star collapses into a neutron star, an ultra-dense object composed almost entirely of neutrons. A teaspoon of neutron star material would weigh billions of tons. The most massive stars, black holes. For the most prominent stars, even neutron stars cannot resist the collapse of gravity. These stars become black holes, regions where space-time is so warped that not even light can escape. Did you know that the elements in your body, such as the carbon in your cells and the iron in your blood, were forged in the cores of stars billions of years ago? The physics of black holes. Black holes are among the most mysterious objects in the universe, where the known laws of physics are stretched to their limits. The event horizon is the boundary of a black hole, beyond which nothing, not even light, can escape. It is not a physical surface, but a point of no return. Singularity, the heart of a black hole, lies the singularity, a point of infinite density where space-time is infinitely curved. Its studying singularities could help scientists develop a unified theory of quantum gravity, bridging general relativity and quantum mechanics. Hawking radiation, black holes, are not entirely black. They emit faint radiation known as Hawking radiation caused by quantum effects near the event horizon. Over stars and black holes. The cosmic cycle. The glassy stars and black holes are not just celestial objects. They are part of a grand cycle of creation and destruction. The elements forged in stars are released into space during supernovae, seeding the cosmos with the building blocks of new stars, planets, and life. Black holes, meanwhile, shape galaxies and redistribute matter, playing a key role in the evolution of the universe. As Carl Sagan once said, "We are made of star stuff." This poetic truth reminds us that the universe's story is our story, written in the light of stars and the gravity of black holes. The eternal dance of creation and destruction, stars and black holes represent the cosmic cycle of life and death, a delicate interplay between creation and destruction that drives the evolution of the universe. Stars, in their brilliance, are born from the collapse of gas and dust within nebulae. They burn for millions or billions of years, forging elements in their fiery cores and radiating light that sustains life on distant planets. Yet, even as they shine, their energy is finite, and their eventual death gives rise to new cosmic phenomena. When a massive star exhausts its fuel, it may end in a cataclysmic supernova, scattering its enriched material into space. This debris seeds the birth of new stars and planets, ensuring that the cycle of creation continues. Black holes, on the other hand, emerge as remnants of the most massive stars, embodying destruction at its most extreme. Yet even these enigmatic entities contribute to the universe's evolution, influencing the motion of galaxies and creating bursts of energy that ripple across the cosmos. This eternal dance reminds us that nothing in the universe is genuinely lost. Every atom in our bodies was once part of a star, and one day, the matter that makes us will return to the cosmos. Creation and destruction are not opposites but partners in the ceaseless rhythm of existence, weaving the universe into a masterpiece of transformation and renewal. The universe's invisible forces, dark matter and dark energy. The universe we observe is only the tip of the cosmic iceberg. Everything we can see, stars, planets, galaxies, and even ourselves, accounts for less than 5% of the universe's total content. The rest is made up of two enigmatic components, dark matter and dark energy. These invisible forces are not merely scientific curiosities. They are the very scaffolding and driving force of the cosmos. Dark matter holds galaxies together, while dark energy drives the universe's accelerating expansion. Yet, despite their profound influence, their true nature remains one of the greatest mysteries in modern physics. Dark matter, the universe's hidden scaffolding. Dark matter is a form of matter that does not emit, absorb, or reflect light. It is entirely invisible and detectable only through its gravitational effects. The evidence for dark matter? The concept of dark matter arose when scientists noticed discrepancies in galaxy rotation. Based on visible matter alone, the outer regions of galaxies should rotate more slowly than the inner regions. However, observations showed that galaxies spin as if they are surrounded by massive, invisible halos. Gravitational lensing, where light from distant galaxies is bent by unseen mass, provides further evidence for the existence of dark matter. What is dark matter? Dark matter is not made of ordinary matter, like the atoms in stars and planets. Instead, it is thought to consist of exotic particles that interact weakly with other matter. Candidates for dark matter include WIMPs, weakly interacting massive particles, and axions, both of which remain theoretical. Did you know that about 27% of the universe's total content is thought to be dark matter, forming the scaffolding on which galaxies and galaxy clusters are built? The role of dark matter in the cosmic web. Dark matter's gravitational pull shapes the large-scale structure of the universe, creating the cosmic web. Without dark matter, galaxies would not have formed in the early universe, and the universe would lack the intricate structure we observe today. Dark energy. the force behind the universe's accelerating expansion. While dark matter binds galaxies together, dark energy works on the largest scales, driving the expansion of space itself, the discovery of dark energy. For most of the 20th century, scientists believed that the universe's expansion, caused by the Big Bang, was slowing down due to gravity. However, observations of distant supernovae in the late 1990s revealed that the expansion is actually accelerating, a discovery that earned the 2001 Nobel Prize in Physics. This acceleration could only be explained by the presence of an unknown force, which we now call dark energy. What is dark energy? Dark energy is thought to make up about 68% of the universe, yet its nature remains one of the greatest mysteries in cosmology. One explanation is the cosmological constant, a concept introduced by Einstein, which describes dark energy as a constant property of space. Another possibility is that dark energy is dynamic, changing over time. This could have profound implications for the universe's future, the role of dark energy in the universe's fate. Dark energy determines the ultimate fate of the cosmos. If it remains constant, the universe will expand forever, leading to a big freeze, where galaxies move so far apart that their light becomes undetectable. If dark energy grows more substantial, it could lead to a big rip, tearing apart galaxies, stars, and even atoms. If dark energy weakens, the universe's expansion could slow and reverse, resulting in a big crunch. Did you know that dark energy is so powerful that it accounts for more than 2/3 of the universe's total energy content? Its effects can be seen on cosmic scales, yet its origins remain elusive. The interplay between dark matter and dark energy are not opposing forces. They coexist, shaping the evolution of the universe in different ways. Dark matter's role in structure formation. Dark matter provides the gravitational framework for galaxies and clusters to form, holding them together against the pull of dark energy. Without dark matter, the universe would lack the structure necessary for stars, planets, and life to exist. Dark energy's role in expansion. Dark energy works on the largest scales, driving the expansion of space and determining the universe's long-term evolution. A delicate balance. The interplay between dark matter and dark energy shapes the universe we see today, balancing the forces of attraction and repulsion to create a cosmos that is both structured and dynamic. The unsolved mysteries of the invisible universe. Despite decades of research, the true nature of dark matter and dark energy remains elusive. They challenge the limits of our understanding, hinting at new physics beyond the standard model, and potentially even new dimensions of reality. What are the particles of dark matter? Scientists are conducting experiments deep underground and in particle accelerators to detect the elusive particles that make up dark matter. What is the nature of dark energy? Is dark energy a constant force, or does it evolve over time? Could it be linked to quantum fields or extra dimensions? How do dark matter and dark energy fit into a unified theory? Understanding these forces may be the key to unifying quantum mechanics and general relativity, bridging the gap between the most minor and most significant scales of the universe. The universe of shadows. The universe is not what it seems. Beneath the visible lies an invisible world of shadows, where dark matter and dark energy shape everything we see and everything we are. They are the silent forces that guide the evolution of galaxies, stars, and planets, holding the cosmos together while driving it apart. As we continue to study these mysteries, we are reminded of how much we have yet to learn. The invisible universe challenges us to expand our understanding, to look beyond what we can see, and to imagine the infinite possibilities that lie ahead. As we move forward, let us explore the ultimate quest in physics, the search for a theory of everything, a single framework that unites all the forces and phenomena of the cosmos, unifying the universe, the quest for a theory of everything. The universe, with all its grandeur and intricacy, operates under a set of fundamental laws that govern everything from the smallest particles to the vast cosmic structures. These laws explain the motion of planets, the fusion within stars, and the behavior of the particles that make up our very bodies. Yet, for all the progress we've made in understanding these laws, one profound question remains unanswered. Can they all be unified into a single, coherent framework? This monumental quest, often referred to as the search for a theory of everything, TOE, seeks to bridge the divide between general relativity, which describes gravity and the structure of space-time, and quantum mechanics, which governs the behavior of particles at the minor scale. These two pillars of modern physics are profoundly successful in their respective domains, yet when applied together, they produce contradictions and infinities, pointing to a more profound truth that lies beyond our current understanding. The search for a theory of everything is more than a scientific endeavor. It is a quest to grasp the very fabric of reality, to uncover the principles that bind the universe together, and to glimpse the elegant simplicity hidden within its vast complexity. The challenge of unification. The challenge of unifying the universe lies in the fundamentally different ways that general relativity and quantum mechanics describe reality. General relativity, the geometry of space-time. Introduced by Albert Einstein in 1915, general relativity redefined our understanding of gravity. Rather than being a force in the traditional sense, gravity is the warping of space and time caused by the presence of mass and energy. This theory excels at describing the universe on large scales. It explains the motion of planets, the bending of light around massive objects, gravitational lensing, and the expansion of the cosmos itself. General relativity has been confirmed by countless experiments, from the precise orbit of Mercury to the detection of gravitational waves, ripples in space-time created by the collision of black holes. Quantum mechanics, the physics of the small. At the opposite end of the spectrum, quantum mechanics describes the behavior of particles and forces on the most minor scales. It reveals a world of probabilities, superpositions, where particles exist in multiple states at once, and entanglement, a mysterious connection between particles across vast distances. Quantum mechanics governs the interactions of particles like electrons, photons, and quarks, forming the foundation of chemistry and modern technology. The incompatibility. The problem arises when we attempt to apply these theories to extreme conditions, such as the center of a black hole or the earliest moments of the Big Bang. General relativity predicts smooth, continuous space-time, while quantum mechanics suggests that space and time are discrete and probabilistic at the most minor scales. When combined, the two theories produce infinities and contradictions, signaling that our understanding is incomplete. String theory. A potential framework. One of the most promising candidates for a theory of everything is string theory, which proposes that the fundamental building blocks of the universe are not particles but tiny, vibrating strings of energy. The basics of string theory. In string theory, the different modes of vibration of these strings determine the properties of particles, such as their mass, charge, and spin. By describing all particles and forces, including gravity, as vibrations of strings, string theory offers a unified framework that incorporates both quantum mechanics and general relativity. Higher dimensions string theory requires the existence of additional spatial dimensions beyond the familiar three. These extra dimensions are thought to be compactified, meaning they are curled up so tightly that they are imperceptible to us. Did you know that some versions of string theory suggest the universe may have 10 or even 11 dimensions? These hidden dimensions could hold the key to unifying the forces of nature. Challenges and criticisms. Despite its elegance, string theory remains unproven. Its predictions are difficult to test directly, as the energy scales required to probe these tiny strings are far beyond the capabilities of current technology. Additionally, string theory is not a single theory but a family of theories, raising questions about whether it truly represents the ultimate framework. Loop quantum gravity, an alternative approach. Another contender for unifying the universe is loop quantum gravity, LQG, which takes a different approach to reconciling general relativity and quantum mechanics. The basics of loop quantum gravity, LQG, suggests that spacetime is not continuous but composed of discrete loops, forming a network or lattice-like structure. These loops represent the atoms of space-time, fundamentally changing our understanding of what space and time are, resolving singularities. By describing space-time as discrete, LQG avoids the singularities predicted by general relativity, such as those at the center of black holes or the Big Bang. This approach provides a framework for understanding these extreme conditions without breaking them down into infinities. Challenges. Like string theory, LQG remains largely theoretical, and its implications for the large-scale structure of the universe are still being explored. Symmetry, the guiding principle of physics. Symmetry is a cornerstone of modern physics, underlying many of the universe's most fundamental laws. It reveals patterns that connect seemingly unrelated phenomena and provides a framework for unifying the forces of nature. The Standard Model of particle physics and the Standard Model, which describes 3 of the 4 fundamental forces, excluding gravity. Did you know that the discovery of the Higgs boson in 2012 confirmed a key aspect of symmetry in the Standard Model? Supersymmetry. Supersymmetry, a theoretical extension of the Standard Model, proposes that every particle has a partner particle with different properties. Supersymmetry could provide a pathway to unifying the forces of nature. Cosmic symmetry is also evident in the large-scale structure of the universe, from the arrangement of galaxies to the isotropy of the cosmic microwave background radiation. The future of the quest. The search for a theory of everything is far from over. It requires breakthroughs in both theory and technology, as well as the imagination to explore entirely new possibilities. Experiments and observations. Facilities like the Large Hadron Collider and gravitational wave observatories are pushing the boundaries of what we can detect, searching for evidence of new particles and phenomena. Observations of black holes, neutron stars, and the early universe may provide critical insights into the nature of spacetime and quantum gravity. Philosophical implications. A theory of everything would not only unify physics, but also challenge our understanding of existence itself. What does it mean to live in a universe governed by a single set of laws? How do we reconcile the simplicity of these laws with the complexity of the cosmos? The elegance of understanding. The search for a theory of everything is a journey of exploration and imagination. It reminds us that the universe, with all its vastness and mystery, operates under principles that are deeply interconnected. Every discovery we make brings us closer to understanding this grand tapestry, connecting the smallest particles to the largest galaxies. As we continue this quest, let us remember that the pursuit of knowledge is not just about solving equations. It is about embracing the beauty, wonder, and infinite possibilities of the universe. Conclusion, reflecting on the cosmos and the physics that shapes it. The universe is an extraordinary canvas of infinite complexity and unimaginable simplicity, governed by unyielding laws and shaped by mysterious forces. It inspires both humility and wonder. Through the lens of physics, we have glimpsed the mechanics of this vast reality, from the most minor quantum interactions to the most significant structures spanning billions of light years. As we bring our journey to a close, let us take a moment to reflect on all that we have explored and the profound questions that remain unanswered. In revisiting the forces, phenomena, and mysteries of the cosmos, we are reminded of the interconnectedness of all things and of our small but significant place in this grand tapestry of existence. Revisiting the forces of nature. At the heart of the universe lies a delicate balance of forces that govern every interaction, from the motion of planets to the fusion of stars. These forces are not merely abstract concepts. They are the very fabric of existence, the invisible threads that hold the cosmos together. Gravity bends the fabric of spacetime, shaping the orbits of planets, the formation of galaxies, and the fate of the universe itself. Its quiet persistence ensures that matter coalesces into stars and planets, providing the stage for life to emerge. Electromagnetism governs the behavior of light, radiation, and charged particles. It is the force that allows stars to shine, rainbows to form, and atoms to bind into molecules. The building blocks of life. The strong nuclear force powers the stars, enabling the fusion of hydrogen into helium and the creation of heavier elements. Every breath we take and every structure we see is made possible by the nuclear furnaces of stars. The weak nuclear force, though subtle, plays a critical role in transformation, driving nuclear furnaces of stars to make every active decay and the processes that shape possible. Without precisely tuning these forces, the universe would be vastly different. Or perhaps it would not exist at all. Gravity's strength, electromagnetism's influence, and the intricate interplay of nuclear forces create the harmony that allows stars, galaxies, and life to flourish. The fabric of space-time. Space and time are not separate. They are intertwined, forming a dynamic fabric that responds to the presence of mass and energy. Through the insights of general relativity, we have learned that this fabric is not static, but is constantly shaped by the motion of stars, the pull of gravity, and the ripple of gravitational waves. Space-time is the stage upon which the cosmic drama unfolds. It bends and stretches under the influence of gravity, guiding the motion of planets and stars. Did you know that gravitational waves, ripples in space-time caused by the collision of massive objects like black holes, carry information across billions of light years? These waves allow us to listen to the universe, revealing events that were once invisible to us. Time itself, we now understand, it flows more slowly near massive objects or at high speeds, a phenomenon known as time dilation. These effects, though subtle, are essential for technologies like GPS and provide profound insights into the nature of reality. The quantum realm, the universe's smallest scales. The quantum realm is a world of paradoxes and probabilities, where particles behave as both waves and points, and reality exists as a series of possibilities until observed. It challenges our intuition and reveals a deeper layer of the universe that is both mysterious and essential. Quantum mechanics governs the behavior of particles and forces at the most minor scales. It underpins the structure of atoms, the flow of electricity, and the chemistry of life. Did you know that quantum entanglement, Einstein's spooky action at a distance, has been experimentally confirmed and is now being used to develop quantum computers and secure communication technologies? At the most minor scales, the universe is a symphony of interactions, a dance of particles and fields that forms the foundation of all we see and experience, the universe's invisible forces. The visible universe, as vast and awe-inspiring as it is, accounts for only a tiny fraction of the cosmos. The rest is dominated by invisible forces that we are only beginning to understand. Dark matter provides the scaffolding upon which galaxies and galaxy clusters form. Without its gravitational influence, the large-scale structure of the universe would not exist. Dark energy, on the other hand, drives the accelerating expansion of space, shaping the universe's future and determining its ultimate fate. These forces challenge our understanding and hint at new physics beyond the standard model. They remind us how much we have yet to discover and inspire us to continue exploring the cosmos. The quest for unity, a theory of everything. The search for a theory of everything, a single framework that unites the forces of nature and explains the cosmos in its entirety, is a quest that spans generations. It seeks to bridge the gap between quantum mechanics and general relativity, revealing the fundamental principles that govern reality. This quest is not just about solving equations. It is about understanding the beauty and simplicity of the universe, finding harmony in its complexity, and connecting the smallest particles to the vast expanse of space-time, our place in the cosmos. As we reflect on the universe's physics, we are reminded of our small yet significant place. The atoms in our bodies were forged in stars. The forces that shape galaxies also guide our everyday lives, and the mysteries of the cosmos mirror our own quest for meaning and understanding. Did you know that every question we ask about the universe brings us closer to understanding the cosmos? Cosmos mysteries mirror our human endeavors, connecting us across cultures, generations, and disciplines. The infinite possibilities of the universe, The universe is a place of infinite possibilities, a realm where every question answered reveals new mysteries to explore. Its beauty lies not only in what we know, but in what we have yet to discover. As we conclude, let us carry the awe and wonder inspired by the cosmos. In all its vastness and complexity, the universe invites us to imagine, ask questions, and dream.